Good morning, all of you. How are you? I hope you are good and got the programming done over the last lecture. Last lecture we have discussed about the reversal of a singly linked list and doubly linked list, various alternates we discussed. So let's have a quick demo of what we have discussed, and then then we can talk of some more discussions today. So just to have a look, first of all, reversal of a singly linked list. The concept which we discussed last time was simple, that I have my head if initially null, I will stop. Otherwise, I'll have a previous pointer, I'll have a current pointer, and previous means current nodes or head nodes linked to be null because minimum one node exists. So after that, we will just iterate. Every time have the current node's pointer to go to the previous. So current's link to go to the previous, but before that, because current link will be lost, so I will have the next node saved, and then previous and current being updated. In the next iteration, next will be updated, and continue like this. When we come out, my current is null, so previous to that is already the last node, and that will become the start node, or that will become the head node. So this could be a simple way of doing iteratively. I also shared with you that this code can be even optimized and may be made even simpler than that, smaller length also, where this if also not needed. So there can be an optimized code. Even if I have a list with empty nodes, still with the same while itself can be handled. I hope in the book also you have studied. So it simply says that I will start one iteration early. I will keep previous to be outside. So previous is not currently being used. And so my next node is currently the head node or current node. So current, I take the last node, that is null. So just one iteration before the previous way I started. So it starts one iteration before, and then that will handle the even empty list also. In next iteration, after first one iteration, current will reach to the effectively first node. So from there onwards, the logic is same as it was earlier. So just it starts accordingly, and it can be done. Then similarly, I'm sure some of you must have attempted recursive that must return node star, and then accordingly you should do. I'm not showing the code. I hope you can try that. For the doubly linked list reversal, all remaining initially logics, so travel forward, travel backward, and then reversal. So reverse with values. It can be void because initial node will not change. If the node is empty or if the list is empty, simply stop. Otherwise, I'll have two pointers, right and left pointer. So right pointer will go to the last node. So this is a code effectively that we used at the start of traverse back. If you see traverse back also, we did like something similar, that I have taken a node and reached to the last node. So here also I reach to the last node. Once I have reached to the last node, then I will need now swapping of the values. But for swapping of the value, when to stop? So for that, I have taken a simple count when I was moving to the right. And if a count is odd or even, accordingly, I need to plan a condition. So I say, fine, count I will decrement every time. So while count is greater than 1, effectively that will be repetition. Why 1, why not 0? I'll leave it to you think for odd as even list, and then accordingly. So left pointer starts with the starting node, and right pointer starts with the last node, and then I'm interchanging the data. So left and right data changed, left shifted, right shifted. In doubly linked list, right shifting became simply possible by this statement. Hence, things become easy for me. And then two nodes have been processed, so count equal to count minus 2, and that's it. And there is no change into the initial pointer, so this reverse value will work simply. And in the main, when we will call, effectively, I mean, case 3 means reverse values called. Again, traverse forward and traverse backward should mean the same output. For example, if I execute this, then if I say I am creating the list, so I'll create it like this. Now, once I have created this, the traversal shows this. If I reverse, 3 is for the reversal. So if I traverse reverse, after this, you can say traverse forward is now 5, 4, 3, 2, 1, and 1, 2, 3, 4 be the backward. So like this, we have to implement and get the verification done. So this way you can do. So then same traverse forward, traverse backward, but the results being reversed start accordingly being used. So this is what you should have done. And now we resume to the next discussions for today's talk. So let's resume further and understand some more related concepts which will be relevant to us today. Let me just focus. Yeah, okay. So I hope the focus is okay now. I'll check once we write. So once we start there, now I'll say, yeah. So some more concepts. So today being the last lecture on the linked list, we will touch the some important remaining concepts of the linked list. So primarily today we are going to talk of four new different concepts. All of these are conceptual in nature. So programming you will do, but I start with the first concept, which I talk of saying concept of something special node and when needed. See, first thing is like you have written lots of codes where if list was initially empty, for corresponding to that, you have to do lot of special if conditions and extra checks, etc., to be done for a lot of situations like this. For example, the best example to understand this could be poly addition, which we discussed yesterday, the demo, and previous lecture we have talked of that logic. In poly addition, effectively, initially I said temp3 equal to null, and then we had a loop, and in everywhere temp3 or star poly3, we have taken those statements and initially kept that the list as null. Just to revise, let me show you the code where we have discussed that part. So this is what code we have discussed last time. So when we said we are going to add two poly, I said, fine, if one of the poly is empty, we have to put an extra condition. So if the poly list is empty, then extra if needed. Not only that, initially I assumed temp3 equal to poly3 or whatever poly3 I'm generating, double star, etc. if I need it, if I have poly3 as a parameter. In this case, I have poly3 passed as return, but temp3 is initially null, poly3 is null. Now, everywhere I have to write this condition. If a poly3 equal to null for equal exponent, same condition needed for if exponent of 1 was greater, same condition needed for exponent 2 greater. Then when the one of the list was non-empty, again needed. Another list was non-empty, probably another needed. More or less the same code I have to write 4 or 5 places, and effectively this was to handle the first node being created. Whenever till now first node was not created, and then it was empty, and that condition was being handled via this code. Then effectively that means just to ensure that first node exists, and because initially first node is null, so we have to effectively always ensure everywhere, and you never know when the first node will be created, under which condition, so you have to put everywhere. So primarily the problem was because of first node non-existing, and correspondingly we have to write this. So extra if etc. needed at multiple places. Similarly, if list is empty, for the reversal, also I have to do that extra if. Not only there, I have done maybe if I say I have traversed backward, there also have to check that. So for null list, empty list, lot of checks, and sometimes it becomes too many of the simple ifs to be put at so many places. It becomes one of the more lengthy code. Sometimes it looks like a lot of probably less organized code. So you might not be very happy to see that, although it's perfectly fine. So one solution to this has been designed. Of course, that solution doesn't come without cost. So one solution to this has been designed in the linked list concept, which is called as header node concept. So what it says is now we will have an extra node at the start of the list. So in this case, if I'm talking of currently either whether singly linked list or doubly linked list, in both cases, any kind of a linked list, if I'm maintaining, I'll say each list anytime always has at the start a dummy node, which we call as a header node. A header node. Now that effectively will mean that this header node is a special node. What does that mean? Anytime if I have a list, even if I have an empty list, that will mean start always points to a special node, which is called as a header node. His data could be just garbage or any empty value, and this null for the time. List with one node will mean start being there, pointing initially to header node, and then whatever data I have. This data field may not be used. If needed, can be used, but it can be garbage. So there is no compulsion to use it because this is a header node, which just ensures that list has always the first node starting after header node. So effectively, if list has, let's say, 5 nodes, 1, 2, 3, 4, 5, then it will mean start is on this node. And from start onwards, the list has all 5 values. This actually means that in all situations, my linked list is always actual nodes or actual list or nodes always after header node. That is the main concept. That actually means that total list. So in this case, I will say list has actually 5 nodes, but header node is extra and it is not counted. That indirectly means whenever you declare any list, you will ensure it to have one header node always. Like if you wrote node equal to start, first statement immediately you will do is give it a malloc. And after malloc, you are going to make initially the list has no nodes. That will mean start arrow link equal to null if it is a singly linked list. And that's it. So this is your header node immediately made. Now any operation call, whether you say call a create or you call any other traverse, insert, delete, reverse, whatever, polyadd, any operation you write, they will use the start, which is pointing to header node always. Now, remembering this concept means that by this process, start is never going to be null. Start is always going to have one extra node. So this is, of course, the cost or disadvantage which I'm making in this case is clear that one extra node memory needed. But advantages are too many. List special conditions just eliminated. And all special conditions simply get handled. Why? List is never empty. Because list is never empty. So, for example, now I say insert at begin. No special checks to be done. Simple. Even start does not change. Insert at beginning will mean data will be inserted after header node. So insert at begin meant this is your header node. This has list might be continued or might not be continued. Even if the list is continued, earlier here, let's say I had 1 and so and so. Now I will say you will insert 11, link like this, but your start always remains to the header node. List was empty, start was here, this was null. Insert at position 1 or insert at begin again meant just this, and then let's say 11 added, and this becomes null. Again, start remains the same. So whatever data is not being used, but no change. Now you can see this becomes a simple case. Not only that, if you say like this, just recall your polyad. Now, earlier everywhere you have to write if a poly 3 equal or temp 3 equal to null. Now this never happens. Because from main itself, whenever you wrote node star poly 3, immediately you gave it a header node. And poly 3 arrow next to be equal to poly 3 arrow link equal to null. That effectively meant this is your poly 3. And from here onwards, actual list will come. Or result of addition of two polynomials. But indirectly meaning poly 3 is never null, indirectly meaning that if condition never needed. And 5 places earlier we have written, all 5 places code becomes simple. No if needed. Every time we can simply say temp 3 arrow link equal to whatever new node I created. And of course, the temp 3 to be updated. And this statement will never fail because header node always existed. Temp 3 was always here. So after this statement, if you have taken temp 3 equal to poly 3, special condition gets handled. Similarly, in the reversal also, reversal will mean if this is your linked list, let's say 1, 2, 3, 4, 5, and then null. My reversal will actually mean all this is changing and this now becoming 5, 4, 3, 2, 1. Even if the list was empty, still the situation will be there, same, because the start will never change. So reversal can be okay. Not only that, even create. You can pass here node star create, node star start or head, and no double pointer needed, can be still void, and header node onwards creation can be done. So all creation will become simple. Outside initially for the first node, whatever extra code we have written, not needed. Simply you can go for the do while loop. And initially no special code needed. Just initialize, and then for first node, no extra needed. So all programming becomes simple and header node will be useful for me. So in case of a linked polynomial, linked stack, anywhere you can use this. Not only that, similarly for the doubly linked list. Doubly linked list will also have always a first node, which is a header node, whose next pointer is also null, whose back pointer is also null. So your back pointer will be also initialized null. Your forward pointer or next pointer will also be null. Both are null, and then list will be created. When you say length of your linked list or how many nodes are there, anytime you do any operation on the linked list, your header node is not counted. So this node is never counted. This is just to handle the kind of a code. Sorry, I forgot to change this. Sorry if you have missed something because of that. So I hope now it is visible what I just wrote. So it was, if I have simply creation node, simply do while will just be used, initially outside nothing to be done. I'm talking of a doubly linked list. I will have these pointers both null and subsequently operated and corrected. Whenever I'm talking length or number of nodes in the linked list, header node is not counted. So we have created, but this is not being counted. Accordingly, you have to modify a bit your traversal also. First node is not to be printed. So you have to ensure that, and that in this case, one node is guaranteedly existing. So maybe you could print using a do while instead of a while do, because one time execution must happen, and then maybe you can have a do while. Internally, you can always skip the first node. So first time, maybe you can always ensure that a temp will be shifted, and accordingly you could do, or any other logic, whatever you want to use. So modify a bit your traversal. Minimum first node always to be skipped, or header node not to be printed. Header node's data is not to be printed. That you have to ensure. So even if you want to use a do while or while, even it can be while. In case of a while, if you want to use, firstly, you will say maybe temp equal to start arrow next instead of simply start. Even that will be a simplest choice, and rest everything remains the same. And in doubly linked list, your backward traversal also will get easily handled because header node will always exist. So all that you can do and improve. So your reversal can be void type. No double star needed, because first node will always exist. Similarly, insert at begin, at position 1, delete at begin. Header node will be never deleted, and you have to ensure that. So modify the code a bit to take care of header node, and rest is done. That's it. So I hope this concept is clear. I need not probably spend more time on this. So this becomes concept of header node. Second concept. We also have a concept related to another additional concept, which I will explain via an example. Like I said, in case of a doubly linked list, you said I had data 1, 2, 3, 4, and then 5. And reversely also linked. This is your start. Now, I say traverse backward. Traverse backward effectively meant you have to take temp to the last node. Only then you could do. So you needed to bring the temp here, and then only it could do. So for that, you needed a loop to take your temp to the last node. That means one iteration extra. Of course, that after that, the traversal. So in terms of time complexity, those who know, this will not be adding to the notation of time complexity, but obviously means First, I have to traverse fully and then display in coming back. So this side display, but because I wanted to go to the last node, I have to do a loop. This loop can be avoided by making the list as a circular linked list. What does that mean? Instead of null pointers to end, which we used to at the last, that will be removed. We will not use. We will say list will have a circular nature. 1, 2, and so 5. 5's next pointer will not be null. It will point to the start itself. So this is your start pointer. 5's next, which was earlier being used as a null, that will point to the start. Similarly, the backlinks exist. Earlier, this link was null. This link will not be null. It will point to the last node. This will mean the back pointer. So effectively start while creation, during creation, you have to do that. During creation, you have to effectively make it circular. And once it is made circular, your pointers are ready to have pointing to this. So advantage. Effectively, reaching to last node is in one step. No loop needed. One step. So earlier I had made a loop. Now, instead of this loop, I will simply say temp equal to start arrow back. Start arrow back means this pointer brings temp here. And that is the way I have reached to the last node. Now I can do the back traversal. So your back traversal now can be done. In one line, you are able to do what earlier you needed, one full step. And if list was empty, of course not. So with the circular list, this becomes advantage and no disadvantage, no extra memory, because node already existed. We have just used the node pointer to point in this way. The only thing is, the earlier we were using null pointers in the linked list. Now, no null pointer will exist. So the another advantage which we will get via this process is that in the linked list, no null pointer will exist if the list is not empty. If list is non-empty. So if the list is non-empty, null pointer will never exist. But it gives me some advantages. This also gives me additional advantages. So what is the advantage? Now, crash via null pointer will never happen. That's another advantage, that code will not crash. Because if at some stage, if you write, let's say, temp arrow data or temp arrow next or back, this code crashes if temp was null. Because via null, if I try to access field, then I was crashing the code. Crash to access the code. Crash if field is accessed via null. Now that problem gets over because null pointer is not existing in the linked list at all. If null pointer is not existing, things become easier for me. Why I am saying if list is null, so I can simply check if a start equal to null, list is empty, so you can handle accordingly. Otherwise, in your list, never null pointer comes. If null doesn't come, you will traverse. Might be you have done wrongly in programming. Even if wrong access is done, output might be wrong. So if you have done wrong programming or wrong steps, wrong or extra looping you have done, in that case, even if extra steps, no crash will happen. Output may be extra, output or looping might be extra, but code will not crash. Because it might happen that while traversing like this, maybe you will come back to this node and this could be again repeated. But crash will not happen. And then that will help you. So your code will never abnormally terminate. Of course, your traversal has to be modified. Your stopping points have to be modified everywhere, wherever you are using null. Like earlier you have written while a temp not equal to null will be incorrect. No, empty list can be separately handled. Otherwise, probably this will become again something equal to temp not equal to start. But if you write this, you are facing another problem. Temp not equal to start is true first time also, and you have not traversed. So first time, how will you handle it? It will be incorrect. So maybe you can think of using a do while so that first node will get traversed. After that, if the condition is true, you can do that. Of course, empty list has to be handled separately, handled before do while. But if it is not empty list, in that case, your do while loop is minimum once guaranteed to run. So you can have this code written here and rest probably you can think of handling via do while loop. Again, I'm not going to write the code. You have to probably think of that. So making your doubly linked list circular gives you advantage that reaching to the last node becomes easy. And similarly, after last node, next pointer brings you back to the start. Although start we have already available. So that's not an advantage, but that's the part of programming and you should take care of this. So there is no null pointer now to stop. When back pointer reaches or when your next pointer brings you back to the start, then you have to stop and assume that the total list has been traversed, etc. So accordingly, you are now you have to take care in insertion or deletion also. Take care of this. No null pointers. No null will be condition at all. Extra if which you are using like insert at the last was happening in case of this doubly linked list. In the case of insert at the last node, because back pointer didn't exist for this, so you had extra if earlier to handle the null situation. Now that extra if not needed because null will never happen. So just make sure that every time it remains circular, to keep it circular always. Rest coding becomes simple. So nothing big change, just you have to ensure this step also. Then the question is, Can singly linked list be circular? Yes, can be. Any advantage? Slight advantage will be there. So singly linked list circular will mean I have here 1, then I have here 2, I have here 3, and so and so. Let's say 5. Now 5 will not be null. 5's next or 5's link will point to the start. Of course, traversal, creation, you have to modify your code a bit to be modified so that this null is not there. Advantage, we don't have any way to go to the last node, so doubly linked list advantage is not that much, but no null pointer still exists in the linked list. In a non-empty list, in any non-empty list, null pointer never exists. That itself is an advantage. Crash via null will never happen. And that's the advantage. And even if you do slightly wrong programming at some stage, this problem will not be coming and code will not abnormally terminate. So with the singly linked list, this is what you will gain. And we probably can handle things in an easier manner. So that becomes your second concept. So when I said your second concept, which we are going to discuss, this was concept related to circular linked list. So now I have discussed the two concepts today. Till now, two concepts discussed. One, header node concept. Second, circular linked list. And both features can be combined where we can have header node also plus circular also. If you feel, you can use that. Header plus circular can be combined. That will mean even if the list is empty, if in case of a doubly linked list, this is your header node. This also, it's for front pointer points to itself. Its back pointer also points to itself. So this is your back pointer. This is your next pointer. And this is your header node. So data is not used. Header node will always exist. And because it's a circular list, so this is going to link to itself. As soon as you add some data to this, your addition of data will also still continue in the same way. In case of a header plus circular, doubly linked list, any node existing will mean this is your header node. Let's say I have added 1 here. So 1's next pointer points to header node. Header's back pointer points to this node, or you can say this node. So this is free, but this is your doubly linked list and start is this. So similarly for the singly linked list also, then can we use this field? Yes, can be utilized. For some situations, can be utilized as long as you don't add any extra loop to have this data. Of course, this is not a data related to your linked list values, but for example, here I could store length or minimum value of the linked list, maximum value in the linked list, because whatever you needed frequently for your processing, that you can store. If you have something special data needed and during processing you are needing that data, earlier we were not having any storage, we avoided taking any extra variable, but now the space is available, so you can utilize this. And Good part is, for example, if I want length to be stored. So initially, you could initialize header your node or start arrow data to be 0. Any new node added or created, you will simply say start arrow data plus plus. One statement. I'm putting brackets. Brackets will be must to ensure the precedence of operators. That will increment your count. So your length is getting actually calculated automatically. Similarly, deletion will mean minus minus. So one extra line only added in your code, no extra loop needed. Wherever we needed this extra line and no loop needed to calculate the length. So your length will be always available. But if you don't need length, you need not store length. If you needed, let's say, minimum value out of this whole total list, similarly, you could store minimum value there. Whenever a new element added, update this minimum. Similarly, you needed max value, you could have max. You needed some highest positive value, store there. Highest negative value, store there. Some prime number you needed during your programming, and that is present in the list or not, store that. So this becomes concept 3. You can use this. And header field or data field can be used in single list also. Because irrespective of a W or single list, singly linked list with header node you can use. In the header, the corresponding data field in singly linked list can also be used in the similar manner. Last concept for today, we are talking of some additional operations on the linked list. You have said, I have given you an assignment, otherwise also you will say you have lots of problems where you are supposed to merge or split 2 linked lists. So this code, if you write in an optimized or efficient way or organized way, not efficient, I'll say, organized way, your programming will always become easier. For example, I say merge 2 sorted lists. Effectively, this is equivalent to in merge sort, you had merge operation, merge function. That always merges 2 lists. In merge sort, in array based, let's say this data was 5, 7, these sorted lists existed 11, 50. Other list existed, let's say 2, 3, 5, 12, and so on. So first what you did, you created a new list. You added one by one all data. So you took 2, then you took 3, then you took this 5, then you took second 5, and then 7, 11, 12. And because your list initially was original list here, this was your array, then you copied back all this data onto this. This is what you did in arrays. You needed extra array because in original array, insertion is costly. Insertion in the original array needed loop. It could not be done in one unit. That was a problem. In linked list, you don't have a problem. Insertion is order of 1 or without loop. So with the linked list, your merge becomes simple. If I say no extra list to be created, extra list creation is also possible. So if I say merge 2 lists into 1, means this list itself should be merged. Meaning that if you have a 5, you have 7, you have 11, you have 12, other list you have a 2, other list you have a 3, 5, and 12. So this was 15. I have 5, 7, 11, 15, and this was 12. So what I really now need is slightly different in the way that my all these nodes should get this. This should become my, let's say, list 1 or list 3. Maybe you could say, okay, I'll have a list 3, but nodes will be reused. This link will remain. From 3, this should first point to this. Current nodes will be relinked. I need this to come here. This link will be broken and it goes to 7, 7 to 11, and 11 to 12, 12 to 15, and 15 to null. Of course, header node and circular also can be used, but this means merging these two lists. No extra malloc. And this all becomes easy in case of the corresponding programming done in case of a linked list. So if I have to do this programming, I should be doing it in a very systematic manner. Then merging for any basis will become clear. Like other merge. Other merge could mean that I have list 1, which has, let's say, node x1, x2, x2. So I have list x, I have list y, which has y1, y2, and y3, these nodes. I want to generate a list Z which merges in a way that x1, then y1, then x2, then y2, and so and so. So alternate nodes linking. That's another merge operation. And like that. So this is another merge. But logic can be simple. If I say no extra malloc, no new nodes, these nodes are to be relinked. How to do? So I can always say merge criteria will be just used to have an if. My logic should be made that this is my list 1, this is my list 2, whether singly linked list or doubly linked list, I will always maintain one temp, one pointer. I will always maintain one temp, 2 pointer. They will be used for comparison or merging condition to be used. And I will say list 3 will be there and last 3 will be always last added node in this. So initially list 3 could be null or there could be a header node and accordingly done. But every time I will say, for example, merge function. This data, this was 5, this was 2. 2 is lesser. So I will have some if condition, the condition. Based on that, I can say first time, list 3 will point to temp 2. And otherwise, you will have, so temp 3 or last 3 also to be temp 3. So my list 3 is now starting from here. List 3 will permanent remain here. Last 3 is the last node corresponding to this, or you could say last, not even last 3, I'll say last one. The last pointer in the output. So last is here. Currently pointing to 2. Next time, my temp will obviously shift. It will come to this place. This is a 3. 3 versus 5 comparison will happen. I say 3 is to be linked. And now because last exists, every time I will say last arrow link to be equal to, in this case, a temp 2. So this was last 3. This link re-established. Earlier it might have broken. Then now temp 2 will further change. So temp 2 will now come to 5. Temp 1 is already 5. Both comparisons, 5 versus 5. temp 1's 5 to be taken, to be linked. So last arrow link updated, and then last will shift to temp 2. Every time last will also be updated. Now this is to be linked. So every time my code is again same. Last arrow link, now it will go again to temp 1. Earlier we had it to temp 1. Now a temp 2. Now I will say it has gone to temp 1. So last will shift to the new node. And of course, temp 2 in this case updated. Now temp 1 will be updated. Go to the next node. Will mean temp 1 from here shifts to 7, and this node still exists. This link still exists. So your temp 1 comes here. So till now what has been generated? Your list 3 is being generated. 2 has been here. 3 has been here. After 3, effectively, it has linked with the previous 5 of your old list, and your last is here. Temp 1 updated. Temp 1 comes to 7. 7 versus this. Now 7 versus 5 will be compared. So 5 is to be copied. That means effectively temp 2. So that will again mean a similar code here. This will mean last will link to this 5. Remember, this link is broken because this has gone this side. So 5 will link to this, and temp 2 shifted. So temp 2 shifted means now it points to 12. So this is your 12. This is your temp 2. And proceed like this. So your merge logic works simple. Now, instead of, let's say, you wanted merge of second operation, we said x1, y1, x2, y2, and so and so. Almost similar logic. Only if will change. First time you will have first node to be linked. Every time your last arrow link will be either equal to temp 1 or temp 2. Earlier, the decision was based on data comparison. Now this could be maybe, let's say, count based. Count equal to odd should mean temp 1, and count even should mean link of a temp 2. But every time this link, and accordingly temp updation, and your if condition will be changing, merge logic based or merge need based. That's it. So all merge for anything. For example, I say merge two lists such that all negative numbers, one list has certain negative and positive numbers, but ordered other lists also have. So all negative numbers to come in one, all positive numbers to come in one, you can do. Any condition, whatever you have, just modify this, rest logic remains the same. And your whole merging process can be copy-paste and reproduced without difficulty. Just explaining few more minutes for the split, and then we will wind up. So in the split also the same process can be done. You have done split of two lists. Again, split criteria could be different. Split of a list into two lists. For example, I have a list, and this has got some data, let's say node x1, then x2, then x3, and so and so. Maybe I say I want to generate list 1 as x1 followed by x3, x5. So I say odd list, odd positioned list. And similarly, I want an even list. That means x2 followed by x4 followed by x6 and so. But no extra nodes to be created. These nodes are to be linked in the proper way. So split a list into two. Other split. For example, my list has some negative and positive numbers, -5, -3, 11, -4, 5, 7, and so and so. And I say split. Negative list to be separate, positive list to be separate. Effectively means this list should get converted into two lists where negative list will mean -3 linked with -5 linked with -4 and so and so, and positive list will mean 11 linked with 5 linked with 7 and so and so. So if that is the case going to be done, my logic will be now simple that again I can have same nodes to be relinked. So it's not that you are going to create any new nodes. No extra malloc. No new nodes or no malloc. That means original list has to be split. Again, I can always say, fine, this is this. So I can always say, yes, that logic can be again simple. I will say initially I will have list 1 to be null, list 2 to be null, and I can have last one to be null and last two to be null. And every time I will say, currently, if I have first node, that will be a separate condition, but first node handling separately. First node for each list, for list 1 as well as list 2. That will effectively mean first node to be seen and handled a special way. But after that, based on your split criteria, so you will have some if, for example, I said alternate nodes. So I can maintain a count being odd or even. Then I will say effectively the logic will be last one arrow link equal to temp1, some temp. So I will always have the next node as a temp. Else it could be last two arrow link to be temp. And of course, that will also mean last one to be updated, last one equal to temp. So this code over, else I will say last two to be linked and then last two to be updated. And based on this, if you will have either the condition, your split criteria mentioned here, this linking done and temp to be always shifted. Temp arrow link. So just repeat this process. You have to loop this and rest of the things will do in the similar way. Meaning, for example, if I had a list of, let's say values were -5, -3, minus say 11, assuming that, let's say here this was +3. So if I have handled the first list correctly, this will become your first list's pointer, negative list. This link will be updated somewhere. This will be your pointer for positive list. Once you have handled your first node correctly, this process has happened. And maybe you are at this step. Temp is here. Obviously, this means this is your last one. And this is also your last two. So your last one and last two are here. 11 being in the positive list, based on the condition, you will say last two arrow link. This link will be established. And now your last two changes here. Last one remains here, last two here. temp to shift. Let's say after 11, I have -4. So temp will change from here and it will reach to this node. Now, this link is currently existing, but this link is currently last is -5. -4 is negative value based on the condition. Last one will be linked like this. So this link will go there and last one updated. So last one is the last node in the negative list. Last two is the last node in the positive list. After -5, let's say I have 5. So your temp will come to 5. And then when the comparison will be done, this link will be changed. So this link you will take to this. So slowly your list is changing. You have -5, then -4, and so and so. This side you had 3, then you had 11, and then you have, let's say, 5. So you can see your list is automatically splitting based on this logic. And this is your negative list, initial pointer. This is your positive list, initial pointer. So this way your split can be. Any other split criteria? The same process you can do. Only the split condition will change. Your logic can remain same. Almost same, only if will change. That's it. So if you smartly write your split and merge logic, all these things will be easy for you. So just wind up. Let's say for your practice, now you must practice all 4 concepts which we have discussed. Your header node use for any operation, including you can store here the length or minimum or maximum also. You can also try your any operation, which is your circular linked list for singly as well as doubly. You can also combine the header node plus circular. And then you should try your various split or merge programs. And all these can be done over singly linked list as well as doubly linked list. So you should try various programs by using these. So all kind of linked list, in both these, you should try various programs. The assignment which I have given to you, it has 25 questions on linked list. All those now can be solved, and all concepts needed to this we have already discussed. So you don't need any extra concept to understand this. Especially this split and merge, if you write in an organized manner, this process will be very easy and you must practice this. So with this, we will wind up the linked list, and from next class, we are going to start with a new concept, and wishing you a great success. And I'm sure linked list practice you will do in a good way and understand all these concepts. Bye-bye. All the best to all of you. Have a good day.